Okay, so now we have to understand what is the condition for maximum efficiency in case of steam turbines, right? So now, as we know, the formula for blade efficiency is basically given by what? Twice of VW1 plus VW2 into U upon V1 square, correct? And this VW1 and VW2 are nothing but VW is total whirl velocity, which I have shown over here. Okay, so I have just replaced VW1 and VW2 by VW. So this is what the formula for blade efficiency which we have studied in the earlier case. So I am just showing you the earlier PPTs for your reference. Okay, so from this particular expression we have calculated the value for blade efficiency. Okay, now what is our target? We need to calculate what is the condition for maximum efficiency of this blade turbine. Okay, now let's simplify this. Okay, but for that we need to understand again the concept of the velocity triangle. Okay, so here if you can see VW is nothing but what? Total whirl velocity, right? So VW1 and this VW2, okay, so if I add these two, we are getting the total whirl velocity, right? So this total whirl velocity, okay, VW1 is from here to here and VW2 is from here to here, right? So if I have to add this VW, or if I have to represent VW, it is nothing but what? VW1 plus VW2, which is nothing but what? BD plus this AB, right? Now I have represented BD plus AB over here. Now if you refer this BD is further simplified as BC plus CD, okay, which I have shown over here. Now if you refer this AB, okay, so AB can be written as what? It is AC minus this component BC, okay, so which is over here. So now this positive BC, negative BC will get cancelled. That's why we can write VW as what? CD plus AC, right? Now for getting the value for CD, let's consider triangle CDE, right? So this CD is right angle triangle. This theta is the angle which is called as blade angle at inlet, and this VR1 is what? It is my hypotenuse, right? So this CD can be written as VR1 cos theta, because this CD is my adjacent component. Okay, so I have represented CD as what? VR1 cos theta. Similarly, if I consider triangle FAC, okay, you can see over here VR2 is what? My hypotenuse. Phi is my blade angle at outlet. Okay, so this AC can be written as what? From this triangle what? FAC, we can write this AC as what? VR2 cos phi, which I have represented over here. So ultimately you just need to remember, we need to write this whirl velocity in terms of the relative velocities and the inlet and outlet blade angles, right? Now in the next step, what we are going to do? We are going to take VR1 cos theta common from the right hand side. Okay, so if I take VR1 cos theta common, okay, what we are getting? Please check over here. Okay, so it is VR1 cos theta I have taken common, so it is 1 plus VR2 cos phi upon VR1 cos theta. Okay, so you can again refer this expression. We have taken VR1 cos theta common, so it is going to be 1 plus this particular term, right? Now as we have studied earlier, this VR2 upon VR1 is nothing but what? It is called as blade velocity coefficient, which is given by K. And there is one more term which we are going to study now, which is what? Ratio of cos phi upon cos theta, right? So whenever I say cos phi upon cos theta, we will represent it as a constant term B. Okay, so we are getting VW as VR1 cos theta, okay, into bracket what? 1 plus this is K and this is B. Okay, now again if you see this VR1 cos theta is nothing but what? This CD. Okay, so from triangle CDE, okay, which we have calculated earlier. Okay, now as we know CD is what? VR1 cos theta. So again we can write this in terms of BD minus BC. Okay, why so? Because this BD, if I consider triangle BDE, this alpha is the nozzle angle at inlet and V1 is what? My hypotenuse. Okay, because this BDE is my right angle triangle. Okay, so this CD can be written as what? BD minus BC, right? So this BD can be given by what? It is V1 cos alpha, or you can call it as VW1, but we are writing as V1 cos alpha, and we know this BC is nothing but it is U. So this CD, which is nothing but earlier VR1 cos theta, can again be written as what? V1 cos alpha minus U. Now what I will do, I'll put this value of CD, okay, in this expression. Okay, so what we are getting, this VW will remain as it is. Instead of this VR1 cos theta, okay, we will write V1 cos alpha minus U, and this 1 plus KB will remain as it is, right? Now what we have to do, ultimately we have to convert this left hand side in terms of blade efficiency. Okay, so what we are doing, we are multiplying by twice U, okay, on the left hand side and right hand side. Okay, so twice U VW is equal to twice U, and this whole term on the right hand side will remain as it is. Okay, now this twice U VW is as it is on the left hand side. Now what I will do, I will take V1 common from this particular bracket. Okay, so if I take V1 common, what we have, it is cos alpha minus and minus. Okay, if you see over here, this U will remain as it is, as we have taken V1 common, so I will divide by V1, and this 1 plus KB will remain as it is, right? So if you can see over here, V1, okay, we have taken common. Now in the next step, what we are going to do, we have to multiply this particular term by V1. Okay, that's why we are getting V1 square, and as we have multiplied, we have to divide by V1. Okay, so in the next PPT, you can see over here, as we have multiplied by V1, so we got V1 square, and this V1 will remain as it is in the denominator, right? Now if you see, in the earlier case, we have one more ratio called as what? U upon V1. Okay, so what is this U upon V1? Okay, in the next PPT you can see I have represented as rho. And what is that rho? It is the velocity ratio which is given by blade velocity to that of the steam velocity at inlet, right? So I will represent that U upon V1 by a rho, and this 1 plus KB will remain as it is. So what we are getting ultimately, it is twice U VW, which is over here. This 2 will remain as it is. Now as we have just studied, U upon V1 is nothing but rho. This V1 square will remain as it is, and the next term will also remain as it is, right? Now as I have told you earlier, okay, we need to take our left hand side as blade efficiency. That's why I'll divide this V1 square to left hand side. So what we are getting, it is twice of U VW upon this V1 square is equal to, this 2 will remain as it is, rho will remain as it is, and the next brackets will remain as it is, right? Now as we know, if you observe carefully, this is nothing but my blade efficiency. So this is nothing but blade efficiency is equal to, this 2 will remain as it is. I'll multiply by this rho to this particular bracket, so it is rho cos alpha minus this rho into rho will become rho square, and this bracket will remain as it is. So ultimately this is what the formula for blade efficiency. Now as we have to calculate the condition for maximum efficiency, okay, so you can see over here, okay, this alpha is constant, K and B both are constant terms. So this efficiency is totally dependent on the velocity ratio, which is blade velocity to that of steam velocity. Okay, so you have to remember this term. The ultimate maximum efficiency is basically given by this particular term. Okay, so ultimately we need to divide it, or we need to take the derivative, okay, with respect to rho. Okay, so if you take the derivative, okay, what we are getting, this 2 will remain as it is, derivative of rho will be 1, cos alpha is my constant term, that's why this cos alpha will remain as it is, this minus sign will remain as it is, derivative of rho square with respect to rho will be twice of rho, and 1 plus KB is as it is, and I will equate this term with respect to rho as 0. Okay, now so this 2 and 1 plus KB will go in the denominator. So what we are having over here, we have cos alpha minus twice rho is equal to 0. So if I simplify this, I am getting rho as cos of alpha upon 2. That means we can say that the velocity ratio is dependent on alpha. Now what is this alpha? This alpha is nothing but what? It is the blade angle at inlet. Now what I will do, I'll put the value of rho in equation number 1 for further simplification. Okay, So instead of this row, I will write what? Cos alpha upon 2. Okay. So what we are getting? This efficiency is equals to, this 2 will remain as it is. Instead of this row, I'll write this term which is over here. This cos alpha will remain as it is, and this minus sign will remain as it is over here. As we have row square, that's why we will take square of this term, which is cos square alpha upon 4, and 1 plus kb as it is, right? So now this cos alpha into cos alpha, we will have cos square alpha. This 2 will remain as it is, and the next terms are again remaining as it is, right? Now you can see we will take cos square alpha common from here. So I'll take cos square alpha common. In the bracket, what is remaining? It is 1 by 2 minus 1 by 4, and this 1 plus kb as it is. Now if you take the LCM of this particular term, okay, we will get the term as 1 by 4 only. Okay, how? By simple method of LCM. Okay, now if you simplify this, this is 2 1s are and 2 2s are. So this cos square alpha will remain as it is. This 2 will be in the denominator, and 1 plus kb as it is. Okay, so this is what is the condition for maximum efficiency of steam turbine, right, in terms of K and B. Now further, if I have to simplify this, okay, as we know, K is nothing but what? It is the ratio of relative velocity at output to that of relative velocity at input, which is nothing but blade velocity coefficient. Okay, and B is what? It is cos of phi upon cos of theta, as we have studied earlier. Okay, now what they have given, if the blades are symmetrical, right? Now what is the meaning of this symmetrical term? Blades are symmetrical means your value for theta and phi will be equal. That means blade angle at inlet and blade angle at outlet will be same. That's why this is theta and this phi will be equal, right? So you can get the value of B as 1. Okay, and if there is no fluid friction, okay, then this VR2 and VR1 will become equal. That's why again your value for K is also 1 when there is no fluid friction, correct? So value of B is also 1, value of K is also 1. So you will put this value over here. Okay, so you will get 1 plus 1. So it is 2. This 2 and this 2 will get cancelled. So the simplest term for maximum efficiency of steam turbine is given by cos square of alpha. That means your total efficiency of the system will be dependent on the nozzle angle, and it is given by maximum efficiency is equal to cos square of alpha. You can play this video repetitively so that you can understand the concept more clearly. Okay, thank you so much. I hope you have understood the basics of maximum efficiency of steam turbine. Thank you so much.